Okay, guys, let's get started. We are almost done with everything. And if all goes well, we can finish this in just the first half of the lesson. Right? So we're looking at proofs here. And this is already a section which doesn't come out very often because if you read at the beginning here, it says proofs. It's kind of like an art because there are certain foundational techniques into working proofs out, but it's not like a one size fits all kind of thing. It's a little bit of trial and error here and there, a little bit of like a brain teaser here and there. So if any of these come out, usually it'll be the more foundational type of proofs, the one where we can just look at it and figure out what to do. So we will look at those today, one of each. All right, so let's get started. I think there's probably 4 or 5 of these, so it shouldn't take too long. The first is called a direct proof, and we already see the explanation for this is not very good. It's obviously in the form of an implication, which is if P then Q, then we have to prove that statement. Whatever P is, whatever Q is, we can fill that in with specific examples. But the way we do that is highlighted in this black box here. And you see it's not very helpful. It says assume P to be true, explain, 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 therefore Q. Right? And that's not, you can see you have to kind of work these out as you go. It's a case by case thing. Right? So we'll learn with an example. The example here says prove all integers n, if n is even, then n squared is even. Right, and clearly this has the form of implication. If something, then something. And let's just make sure we understand this. If n is even, that's P, then n squared is even. That's Q, right? This part in the beginning which says for all integers n, that's really just additional information, right? It's not a part of the implication, but it's there. So we have a restriction on n. So this first part here is P, the other part here is Q. Okay, so let's just let that sink in for a moment. If P, then Q. So remember, as we said, we start by assuming P to be true. And from there, we need to mathematically deduce Q. So that's the way we do these things. All right, so assume P to be true. Somehow explain, 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 which is the mathematical process of using our logical operations. And then we get to Q. So how do we write this down? How do we write P down mathematically? Anyone has any ideas how to write an even number mathematically?
Something like
You guys are on track? Someone said something in the back there?
anything over 2.
Anything over 2. That is not incorrect. That's actually right. Yeah.
Not incorrect.
Not incorrect. So the way I write it is a bit different, but it uses that idea. The way I write it is n is equal to 2 times k, where k is some integer. So it's the same thing, it's divisible by 2. Yeah. So we can see in this form here, n is always even. No matter what integer you substitute here, this will give you an even number. Right? Take some examples. If I sub 1 here, we'll get 2 as a result. N is 2, that's even. If I sub -3 here, you get -6, which is even. No matter what you do, this is even. Right? So this is the universal way to represent an even number. So from there, can we prove that n squared is even? Well, if you just square both sides of the equation, you'll end up with n squared. And then we have to somehow show that it has the form of an even number. Right, so let's do that. That's the explain, explain, explain part. So from here, let us square both sides. That seems like the most logical thing to do. Square both sides, and we get n squared is equal to 2k in brackets squared, which is n squared is equal to 4k squared. Right, that doesn't exactly help us yet, but what we can do is pull a 2 out, right? Because we want this to look in a certain way. N squared is equal to 2 into 2k squared. Right, that's the trick we have to do here. And the reason I do that is because we know k is an integer. So if you square an integer, you also get an integer, right? So whatever's in here is an integer. So essentially what we've written is 2 times, let's call this something, let's call it 2 times j, where j is an integer, right? Defined by 2k squared. We can just put that there so we know. So in essence, what I've showed is n squared is equal to 2j, where j is an integer. Let me just summarize that on the side. N squared is equal to 2j, where j is an integer. And we know that this is the form of an even number, right? We started with 2k, where k was an integer. So this is the same thing. Doesn't matter what we call it, k or j, doesn't matter, it's still an integer. So by showing this form, we've shown that this is even. So long as you end up with something that says 2 times an integer, then you are even. So let me just make the whole thing visible. Okay. So I'm going to leave that up for a moment. I'll let you guys digest that and ask questions if you need to. Just note the form in the beginning and the form in the end are the same form, right? So we start with even and we prove that we are still even if we squared. People don't usually like this section because you have to kind of memorize the tricks here. So far, we all okay? Okay. All right, so that's proof number 1. Done. Again, just practice this at home if you need to. Let's see what's the second one is proof by contrapositive. All right, so this is what we use when a direct proof doesn't work. Sometimes this is more helpful. So recall that a direct proof is where we try to prove something of this form. If P, then Q. But we know that an implication is logically equivalent to its contrapositive, meaning it's like the same thing. It's written in a different way, but it represents the same thing. And the contrapositive looks like this at the bottom here. Not Q, no, sorry. If not Q, then not P. That's the contrapositive. So essentially, because we know these two are equivalent, if we can't prove the original box above, that's a direct proof, then maybe a next thing to try is to prove the one below, which is the contrapositive. So that's what we will do here. But first we have to prove the original doesn't work, or we have to show at least that it's difficult enough to motivate trying this new method. So let's try this example at the bottom here. Let's try the original way, and then we'll see if it doesn't work, then we'll go to contrapositive. Okay, so we're given a statement that seems similar to the first one we read. All integers n, if n squared is even, then n is even. So we've identified our P and Q here. If n squared is even, so n squared is even, that's P, then n is even, that's Q. All right, so can we, in the original way, we assume P, let's just write that, assume P, dot, Q, assume P, explain, therefore Q. That's the original way, and let's see if it works. So P says n squared is even, so I will write n squared as 2 times k, right, as we have done before, to represent an even number, where k is some integer. Now, how can I then get to show that n is even? I would think take the square root of both sides, right? So we get to n. So let's try that. Square root of both sides, square root of n squared on this side, square root of 2k on this side. And again, we're already being a bit loose with the rules here because I technically have to write this as absolute value n. So that's already a bit of trouble, already not so nice. And this side we will get square root 2, we can't simplify much. Square root k, can't do much. So it's already a bit of trouble here. We can't really go further. I mean, we probably can. There is a way, definitely, but it's probably too difficult for us to stress about when there's an easier method. So this shows us we should probably ignore that and try the contrapositive. So the contrapositive would be, which one was first? Q or P? Q, right? So it switches the order. Not Q, arrow, not P. Okay. That means we're starting with not Q. So Q says n is even. So not Q will be n is odd, the opposite of it, right? Not P. So P says n squared is even. So not P will be n squared is odd. Right? We're just making them opposite of what they were originally saying. And now can we prove this right here? I think that should be a lot easier to prove than what we were trying already. Right? So does this step here make sense to you guys? Just constructing the contrapositive statement. Okay. If we're struggling a bit with this, we did this stuff in learning unit 3. If you need a recap, you can go back to that at some point, not immediately. If you forgot it now, that's okay. All right, so let's start by assuming n is odd. Explain, 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 then get to n squared is odd. And that shouldn't be too bad. So n is odd. I will write it like this. Now let's think for a second. I can write it as n is equal to 2k, which gives me an even number, plus 1 will give me an odd number. So just add 1 to an even number, you get an odd number. So this shows us the thing is odd. We must also say k is an element of integers to be specific. From here, can I then square both sides and show I get an odd number? I hope I can. Let's try it. Square both sides. Let's say that. Square both sides. Then we get on this side n squared. On this side, we get 2k plus 1 squared. Open it up. N squared gives us 4k squared. I'm going to do this in one go. You guys can slow down if you need to. 2k squared plus 2k plus 2k, which is plus 4k plus 1. Okay, does that look like an even number? Not yet, but maybe we can try and manipulate it to get it there. I think we pull out a 2 from here. Let's bring this up here. N squared is equal to 2 into 2k squared plus 2k plus 1. And because k is an integer, k squared is surely an integer. A linear combination of integers gives us integers. The 2's in front are integers, so it doesn't change anything. So this entire thing here is made up of integers, so it is an integer. So that means we can write it as n squared is equal to 2j plus 1, where j is some integer. And we can specify j is equal to 2k squared plus 2k, just to be specific. But this form here is what we are looking for, because we see it has the form of the original, which is odd.
That's one.
Sure, that'll work well. Yeah, it must work. Hey guys, any questions so far? Is everyone just eager to be done with the syllabus now so we can let us happening? Okay. Or if you guys need to stop me, just stop me. I get a vibe that you guys want to watch the recording later in your own time and understand this. Yeah.
Come on, bro. That's how we can share.
Okay, proof by contradiction. Now there's a long story here that explains how this works, but it's best explained with an example. And the idea is not too difficult, right? So we can come back and read this at some point if we need to. But in the example, we'll see that essentially we look for a contradiction here as a part of the proof. So this is not usually written in the form of an implication. Not usually. Maybe it can be, but it's not usually. So let's look at the example. Our example says there are no integers x and y such that x squared is equal to 4y plus 2. So we have to find a contradiction here essentially. It says there are no integers x and y such that the formula holds. So we try and prove that there are integers x and y such that the formula holds. and find a contradiction there. Right? That's how this works. We assume that they are wrong, essentially, and then we find a contradiction, which means, okay, they must be right. That's the idea. Okay, and it works on the basis of the structure of implications and doing strange things, which we can look at some point. But for now, to avoid confusion, let's stick with this example. Okay, so there are no integers x and y such that this formula holds. So assume there are integers. Assume there are integers. X, why am I writing like I can't write? X and y such that the formula holds. So assume that these integers exist and then find a contradiction. Now that's very broadly speaking, find a contradiction. You could find a contradiction because it breaks something that we know must work, like left-hand side must equal to right-hand side, or even number must be even, something like that, you know? So let's see if we can find a contradiction here. Okay, so if there are integers x and y such that the formula holds, remember guys, some of these things I haven't looked at, so even I'm trying to work it out as we go along. If you guys have ideas, you can chip in as well. There are integers x and y such that. Okay, so if there are integers x and y, it means that we assume the formula holds for integers. So that means let's express x and y as integers, I guess. Okay, so if I remember correctly, I think this formula uses proof we did in the previous question, which is not always nice, but anyway, let's see. So x, if I can write x as some integer, doesn't say order even, x as an integer. That's the x by 4y. What if okay, I'm not sure if I remember where to start here. Does anyone have any ideas? Why such that? So how do we find a contradiction? All right, instead of wasting too much of time, let me see how they start. I'm sure this thing is in the module manual, right? Let's check what they did and get a start from there. This is why I don't like the proof section. There's too much of brain teaser stuff going on. Let's go to IIE, ITE 2025. Let's find our module manual. Let's check how they start this thing. So this is the one. Oh, we're here already. Okay. So, okay. I think I see what they do here. So because of the form of this, they're saying that we can write the right-hand side in a way where we pull a 2 out, and then we end up with 2y plus 1 here, which essentially means that x squared is even, right? Because this is 2 pulled in front of an integer, right? So that means this is even. It's even, I'll put in brackets here because this is 2 times j, where j is equal to 2y plus 1. You don't have to worry too much about that. That's just to help us see why it's even. So that is even. And squared is a bit high up. Let's bring it down. X squared is even. So yes, we proved in the previous question that if x squared is even, then x is also even. We proved in the, so let's note that information. So already proved that if x squared is even, then x is even. Okay. So we've already proved that x is even. So that means I can write x as 2 times something. Let's call it 2n, where n is some integer. Okay, that means I should be able to square what I have here and equate it to the top and see if we find some contradiction. And I'm hoping we do there. Let's see. So can I square this at the bottom and write x squared is equal to 4n squared, and then equate this and this because both are x squared, so they both should be the same thing. So equate these two, and then I'll get, let's see how we write this now. I'll write this on the left, 2y plus 1, that comes from the top, 4n squared, that comes from the bottom. Okay, and okay, I think I can see where the contradiction is coming in. We can divide both sides by 2. Divide by 2 and we get 2y plus 1 on this side and 2n squared on this side. Right? And although it may not seem like we've gotten anywhere, this is the contradiction already. That is because the left-hand side is an odd number. It's 2 times an integer plus 1. And the right-hand side is an even number. It's 2 times an integer. So something odd cannot be equal to something even. That doesn't make sense. Right? So this is the contradiction. The step here. Let me leave that up for a moment. Hey, did I lose anybody anywhere here? I'll leave this up for the moment. You guys can take it down, take pictures, whatever you need to do. Also, I don't like this section because you guys can actually see my brain working in real time, trying to figure these things out. And you guys may think, shouldn't say this on video, but if you speak to lecturers, like you hear the discussions in the lecturers' lounge, lecturers all have techniques for when they get stuck in front of a classroom, how to turn the blame to you guys. That's like a thing. No one wants to be in front and act like they don't know what's happening. So it's like if you ask a question they don't know, they'll be like, you should know that, or maybe you should look that up and tell me because that's something you guys should know. There's always a story, right? So just guys, don't say names, the recordings. You shouldn't be giving our secrets away, but yeah. I'm the union leader, yeah. Okay, so this is one where there's no example because it's really that straightforward. And this is, I don't think this can be tested because it's just like it's something that could take you 1 second or 2 years. There's no in between with this thing, right? So proof by counterexample. This is where you get a situation where you're making some kind of existential claim. Like this example here. Again, we look straight in that example. The example says, if we want to prove, there's it right here, there is an integer n such that n squared minus n plus 41 is not prime. So in other words, we want to prove that for this formula, n squared minus n plus 41. We'll see what are we proving is not prime. So the claim is that this formula always gives out prime numbers. Always outputs a prime number. And the claim is that we can find an n, for which we get something which is not a prime number. So to prove that, you have to just find that n. That is just a matter of substituting a whole lot of different n's into here and looking for one which is not a prime number. And you can see this table, they've done a few for you. If n is 1, you end up getting 41, which is a prime number. If n is 2, you get 43, which is prime, and so on and so on. They've tried many n's and they haven't found a prime number. I mean, they haven't found something which is not a prime number. So if you find that one, you've proven this. That's all it is, right? This is why I say you can find it immediately or you can struggle for a long time. So I don't think there's a really fair, nice way to test these. Okay, you guys all okay with that one? All right. Again, the summary is here. It's a short summary to read if you forget it. And now we have the last one to do. This is the last mathematical thing you guys will probably see in your whole lives. Unless you study maths further, but many of you don't need to. Okay, so let's try to enjoy this one as much as we can. And this one is a bit more logical, so we can deal with this one. Proof by cases is similar to what we were doing for direct proof, except here it may not be obvious how to go about something like this. So we may say something like, let's say we want to prove something is true for all even numbers. And that's a difficult thing to do. So what can we do? We can break even numbers up. Okay, no, let me think of a different example. Let's say we want to prove something for all integers, right? That's a better example. If you want to prove something for all integers, it may be difficult, but if we break it up into even integers and odd integers, prove it for even integers and then prove it for odd integers, we'll essentially prove it for every possibility. So if there's something that you can break up into categories which represents the entire thing, you can use those categories individually, prove it for each one, and then you can say that's it, and we're done. So that's what we will try to do here. And I hope this one is not too difficult, but let's try it. For any integer n, the number n cubed minus n is even. Okay, so let's see how we tackle that. For any integer n, the number n cubed minus n must be even. So for any integer is different. I think we'll do exactly what I said here, right? So let's try and break it up into even and then odd numbers. So this is the claim above here. So start by assume n is even, and let's see what happens. So assume n is even. That means we write n as 2k, where k is an integer. Let's just say k element of integers. Then I substitute that into the formula above, and I end up getting 2k cubed minus 2k. Now we have to show that this gives us something even. And will it? Let's see. So 2 cubed is 8, k cubed is just k cubed minus 2k. I guess I can pull out a 2 from here and write this as 4k cubed minus k, which is 2 times some integer, which is even. Right, so we've reached that place where we can say this is. Well, let me just do that thing for completeness. Running out of space here. I can't scroll up further because this is the last slide. So let me bring this up here and say that's equal to 2 times j, where j is some integer, and we know that j is 4k cubed minus k. So getting to this form here, 2j, as we know, that proves it's even. It's 2 times some integer, which means even. Okay, so that's done for the case where n is even. We show that n cubed minus n is even. So now we need to show this for the odd case as well. assume n is odd, and let's see what we get. So we've assumed n is even in the beginning, and we did that part. Now assume n is odd. And I don't know how this looks like it's going to be a bit tricky, but let's just try it. So if n is odd, it means I can write n as n is equal to 2. What didn't I use yet? K, let's use L. Okay, that doesn't look like an L. Let's use M, 2m plus 1, where m is some integer. Now I have to substitute this into the formula, and that's going to be a little bit tricky. So substitute. So n cubed minus n becomes 2m plus 1 cubed minus 2m plus 1. So we've got something cubed here, which is going to be a little bit lengthy to work out, but let's just see, is there a shortcut here? Is there something we can do quickly? I can factor this out. Does that help us? I don't think so. Let's just work it out and see what happens. Okay, so I'll get 2m plus 1 on the outside. Then I'll end up with 2m plus 1 squared. Okay, let me just write it so I don't lose anybody. Minus 2m plus 1. That gives me 2m plus 1 into 4m squared plus 4m plus 1 minus, I'll just distribute the minus in and get a 2m minus 1. Now if you use FOIL again to multiply the outside 2m plus 1 into the already expanded bracket, and that's going to be a bit of a story, but let's do it. So that will become 8m cubed, first term. Second term becomes 2m times 4m becomes, so I messed something up already, no, 8m squared. 2m times 1 is 2m, then plus 4m squared. This is all times 1, so it doesn't really change anything. Plus 4m plus 1 minus 2m minus 1. Okay, we have to show that this result is now even. So let's simplify as much as we can. 8m cubed, I can't do much with that. How many squared numbers do we have here? We have an 8 and a 4, so that's going to be 8, 9, 10, 11, 12 m squared. That one and that one gave me 12. We got a positive 2m and a negative 2m, those cancel. We have what's left here. 4m plus 1 and minus 1 cancel out. And I think that's key here, because that plus 1 minus 1 should get rid of odd possibilities, I think. I don't know. Let's see where it ends up. Actually, yeah, because m is an integer. So that means I can factor 2 out and be left with some integer after that. So if I factor 2, I'll be left with 4m cubed plus 6m squared plus 2m. And because that's a linear combination of integers with integer factors in front, and integer powers is still an integer. So this at the bottom is essentially some integer. It's 2 times, what name can I use now? I'll just use L. 2 times L, where L is some integer. And L is given by whatever's in the brackets here. 4m squared plus 6m squared plus 2m. So it's this part here that I'm underlining. That is the main part of the proof. And so we've shown for the odd case, we get something even, and for the even case, we get something even. So we've done it for 2 cases. Odd and even are 2 cases which encapsulate all integers, right? So that means we've proven for all integers. I can just feel the eagerness to be done in this class. Okay, any questions so far? Okay, even if you guys don't fully get it now, do you think it's manageable for you guys to recap the stuff? Sounds. I hope so. Okay, anyway, we still have more sessions after this. Those sessions will become study sessions. So you guys come here and then you can work on whatever you want, and I'll be here if you need help. And we'll allocate one of them, maybe two of them, to go over past papers. Yeah. And if you guys have any suggestions of other things you want to do, you're welcome to suggest. Okay. Then, yeah, that's it, guys. We're done with the syllabus. Well done, everyone, for making it through. And yeah, we can call it off here. There's nothing more to do.
Thank you so much.
All right. I'll be here for some time if you guys have questions as well, though. We'll be here.